There is some knowledge out there about these more advanced systems, of which sarin is one of them. Unfortunately, terrorists can get hold of it. I've got a molecule of sarin here.
Not real sarin?
Not real sarin, no, that would be illegal to make that. I've made it out of straws and these coloured balls here. Quite a small molecule, not many atoms, and that's why it's volatile. It's a gas, or a very low boiling liquid. Here we have a phosphorus, this purple one. These two red ones are oxygen, the black ones are carbon, and the thing which makes it reactive and volatile to some extent is this one here. This is a fluorine. And what this does is it blocks something in all animals, humans, called acetylcholine esterase. That's what it works on. So what is acetylcholine esterase? Well, before I tell you what the esterase bit means, I'll tell you a bit about acetylcholine. So this is a molecule here of acetylcholine, and this is a neurotransmitter. So whenever we breathe or move our arms or do a whole range of things, heartbeats and whatnot, we use our nervous system. And our brain sends a signal. Now, throughout most of it, it's like an electrical cable, but when it gets to a junction, those signals are transferred by neurotransmitters, and acetylcholine is one type of neurotransmitter. So this drifts across the synaptic gap, the junction, and it triggers the next response, and that response might be the arm moves or lungs breathe. When you want that response to die off, what happens is this drifts away from its receptor, and a molecule like a Pac-Man comes along and chews this up, and that molecule is called acetylcholine esterase. So that's the totally natural, very good thing, because otherwise, if you move your arm, it would always be there. You wouldn't be able to stop it and get it come back. And again, with breathing, you'd be always breathing out and not breathing in. So you need this to go on, and this happens, in milliseconds. It's incredibly quick. And all that happens is that this acetylcholine esterase comes along and it takes that end off. This is now vinegar over here, and the other bit is choline, and that gets recycled to make more acetylcholine in the receptor end. So that process is going on and on and on constantly in our bodies. And what sarin does is it comes along, and the molecule which takes this end group off here, let's call it this thing here, it's this OH which is going to happen.
That's the Pac-Man, is it?
That's the Pac-Man molecule. Comes along, it swaps that for that, and then water comes in and takes this off to make acetic acid. Well, sarin comes along and it's got a much more active group. The fluorine is really reactive. That goes, and this attaches on, but now water can't take this off again. So it's just soaked up one of these Pac-Man molecules, acetylcholine esterase molecules. Well, now you see it's not available to break down the acetylcholine in your body. So you've always got an on switch on your muscles, and the thing which is deadly is your breathing, because obviously your lungs and muscles, they move in and out, and if they don't go one way and don't go back the other way, then you'll very quickly die of suffocation, which is why you see in all these news reports people with really bad breathing problems, and it's because they can't get those muscles to work correctly, because the acetylcholine esterase is being mopped up by the sarin, and the water can't hydrolyse. So there is an antidote, and of course whenever chemists have designed in the past poisonous things, obviously they don't want to kill themselves. They're clever guys, they invent some sort of antidote, and the antidote is this molecule. It's called praldoxine, and this is like super water. So here's an oxygen here, and it's connected to this nitrogen, and that makes this oxygen about 100 to 300 times more reactive than normal water, and that can come along and displace the sarin from the acetylcholine esterase, and that can go about its business again.